Today I'm going to a magical place to investigate a geologic mystery. I'm driving to the base of the magnificent Beartooth Mountains of Wyoming and Montana. The mountains in the distance naturally draw attention, but for today I want to investigate these smaller mountains in the foreground. They seem out of place. Why are they isolated out in front of the main mountains?
Hello, I'm Myron Cook, and I hope you've been having a good day and continue to have a good day. I know I'm having a good one because I'm outdoors with the rocks, out in this wide open country, looking at mountains back here, and then I have this interesting rock here. Now this mountain that I'm adjacent to, I've been curious about it for some time. I've wanted to take a closer look at it. It seems anomalous to me to have a couple mountains sitting out in front of the mountain, say a couple miles or so, the big mountain. And so here I am. And what do I see? Well, I'll make a couple observations and then I'm going to let you make some on your own here. But these clasts here are limestone and dolomite. These cobbles and pebbles and even down to almost, well, I'm sure there's sand-sized particles in here as well. All in a big mix, very poorly sorted because it's such a wide range of sizes, of clasts. Cobbles here mostly. And they get up to bowling ball size, I've seen them in here. And another interesting thing is they tend to sit, these cobbles, the larger ones, tend to be sitting in a matrix of finer material. So that's an introduction to this outcrop. Now let me show you some photos and a bit of drone images, some drone shots, and let you make some observations on your own. Just some basic ones, because I think they're going to help us unravel this mystery here.
This photo clearly shows that the cobbles are embedded within a fine-grained matrix of mud and sand. This is referred to as a matrix-supported conglomerate. How do you think that happened? One thing I think we can say with confidence is that they weren't deposited in a river. Let me explain. What we observe is shown here on the left as matrix-supported. The gray clasts don't come in contact with each other. They're floating in the matrix shown by the blue dots. The matrix is typically composed of mud and silt-sized particles. On the right is a sketch of clast-supported conglomerate where the clasts do come in contact with each other, and the matrix simply fills the voids. Clast-supported conglomerates are always deposited by water, such as in a river or on the beach. We'll talk about the deposition of matrix-supported conglomerate later. What are you noticing? It really is an impressive mountain of clastic material, isn't it? Geologists use the word clastic to indicate rocks that were created by the breaking up of older rocks. This includes rocks like conglomerate and sandstone. We've been focused on this mountain along this side here. This mountain is very similar to the one we've been examining and most certainly was formed by the same processes.
Now that we've had our first look at the outcrop here with these interesting cobbles and things, and also the drone shots and photos, etc., and I hope you've enjoyed making some of your own observations, with that first look, now I think we need to look beyond the mountain here, beyond these outcrops, and take in some information around the area. That almost always seems to be critical when you're unraveling a geologic puzzle.
There is a ridge that lies between the two mountains that I think we should take a look at. What do you think of these deposits that I've been walking around on? These boulders, some of them the size of small cars, I think are an important clue. I'm standing right here. If you look closely, you can see faint arcuate ridges within these deposits. From a higher view, we see the deposits that we've been studying in this area. There's something else I want you to see here. Look carefully. I recently mentioned arcuate-shaped ridges. I've highlighted the most obvious one. They're quite distinctive, aren't they?
I'm sure there are a bunch of you that have figured this out, especially of those of you that live to the north. If you're into geology anyway, if that's a hobby of yours, do they look like glacial deposits, like moraine deposits? Yep, that's it. And congratulations to those of you that figured it out before I told you. Yes, all these big boulders, some of them car-sized, scattered about, within all this finer material. It's all unconsolidated, not cemented together. And this ridge that I walked on is a terminal moraine, so they're glacial deposits.
Here we see a small terminal moraine in Jasper National Park of Canada. These are typical moraine deposits above Lake Louise in Canada. A nice example coming from Nepal of large lateral moraines as well as a large terminal moraine. Now we know what these lines are. They're small recessional moraines, moraines that developed as the ice receded back towards the mountain. You can almost see the ice there.
Well, that was relatively easy, wasn't it? We figured out that these deposits are glacial, and these mountains here that we've been looking at on either side, certainly they're glacial. That would make sense here. We have the terminal moraine between them. Although these mountains are quite a bit taller, and they are a bit different, are we sure that those could be glacial? They have similarities, don't they? But we have this kind of obvious association. I think we need to think about this a bit more and make some more observations, because I'm not so sure. And this is the way science works. We find these ideas and we try to get comfortable with them. Sometimes it takes a while.
The moraine deposits are very poorly sorted with rocks of various sizes within it. We also see that in the outcrop of the mountains. There are a couple of important differences. The moraine deposits are unconsolidated, whereas those of the mountains are consolidated or cemented together. A nice view contrasting the moraine deposits from those of the mountain. There's a critical difference between these two deposits that I hope you notice. We'll come back to it later. I think it's time to investigate the larger mountains.
Wow, is it windy up here? I mean, whew, I can't fly my drone here, unfortunately. I might try it a little, but it's super windy. But notice these spectacular formations of rock that are dipping so steeply behind me. In fact, as we go in that direction out towards the basin, they become vertical and even overturned. They're so steep. But I came here because the composition of these is limestone and dolomite, of these great cliffs through this area.
Looking across the valley, we see another perspective of this spectacular mountain. The cliffs are all made of limestone and dolomite. This uplift occurred during the Laramide orogeny starting at about 65 million years ago.
And that should offer you something to think about. It's like, well, this is a huge high mountain, and just down that way 2 miles are these smaller mountains that we've been looking at. And they have a lot of limestone and dolomite cobbles in them, if we'll remember. So I think it's completely reasonable to think that this formation, these limestone and dolomite formations, are the source of the material for that.
This observation seems to fit the hypothesis of the mountains being terminal moraine deposits composed of materials scoured from the distant large mountains in the background. Let me sketch out what the ancient glacier would have looked like. In this scenario, sketched in blue, we have a large glacier, and I do mean large glacier for a mountain glacier, coming out from the mountains and building this terminal moraine. Some of the moraine has been eroded away, and this is just what's preserved. But the moraine material here, these mountains in front in red, they're about 1,000 feet tall, so the ice thickness would be at least that, and that's an impressive thickness. In this hypothesis, the lateral moraines which surely existed have been completely eroded away, which I find a bit odd. To the south, near Pinedale, Wyoming, on the south side of the Wind River Mountains, we see a spectacular example of intact moraines of a very large mountain glacier. I say large. The terminal moraine is about 500 feet tall, which is about half the height of the hypothesized one we've been talking about. We've made several observations that seem to indicate that this mountain is an ancient glacial moraine, a terminal moraine. Are we comfortable with that?
Yeah, I'm not so sure I like the thought of these being glacial moraine deposits or any kind of glacial deposit. What do you think? I'm uneasy about it. And you're asking me, of course, well, Myron, why are you a bit uneasy? And I look at these, the sorting within them. Yes, they're very poorly sorted. The moraine deposits are too. But we don't have these big clasts, these huge, sometimes car-size boulders in here. They all tend to be grapefruit size or smaller. So that bothers me.
It also bothers me that this is such a large moraine, yet we have no preserved lateral moraines. Furthermore, it's much larger than the obvious moraine deposits that we studied earlier here. There are several other problems that I won't get into.
But there's one other basic observation that I know you made when you were looking at the drone video. I asked you to look at the bigger picture and make observations.
Looking at the mountain again, I haven't mentioned the layering within the deposits, which I know you noticed. As a bonus, did you observe the change in dips? In the lower section, the slope is about 70 degrees or more, whereas in the top it's as shallow as 20 degrees. I have a feeling this is telling us something interesting.
Do we have layering in glacial deposits? Well, sometimes in the fine-grained outwash deposits way out in front of the glacier, even beyond the moraines, yeah, you can get some layering, but it's hard to do it in this coarse material, or to see it, I should say, or observe it in glacial processes or in glacial deposits. So this, I think, is really hard to say that you could put all these layered deposits in with a glacier. Boy, this puts us right back to square one.
We need to think of depositional systems or processes that create dipping layers of coarse-grained materials sloping down and away from a mountain. Isn't this a fun process? Just thinking, imagining, what could it be? I can only come up with one reasonable option. Alluvial fans like we see here in Death Valley. They transport material away from the mountains out onto the valley floor, and the top of these fans, of course, slopes down and away from the mountain. Each fan, of course, is unique, but they're often associated with debris flows, which is essentially a mud flow mixed with lots of rock. The resultant deposits are matrix-supported conglomerates like we observed in our outcrops. Looking down Death Valley, we see many alluvial fans on both sides. They're so close together that they actually coalesce. I mentioned earlier that the changing dips in the strata could be very informative. We noticed that the lower units are dipping much more steeply than the upper ones. In fact, if you look carefully, you can see that there is a rather abrupt change in dips at about where I've drawn the green line. One has to wonder why this occurred. Question: do you think the steep dips of 70 degrees and even more reflect the slope of the ancient alluvial fan? I'll give you another clue. These deposits are about 60 million years old, which is right during the uplift of the larger mountains during the Laramide orogeny.
Well, I think it's time for a whiteboard to sketch, and I've got a cross-sectional view looking sideways. So I guess I need to sketch my little tree over here. I'll put a conifer right here. Okay, here we go. Now that we have that, we understand what we're looking at, which of course is a big mountain here, the alluvial fan here in red with these dots representing the coarse grain material within the fan, generally coarse grain. And I want to make a comment about these debris flows. I don't want to mislead you into thinking that fans are composed of debris flows. They can be, and significant portions of them can be, like we've observed, but not necessarily, depending on the fan, the climate, the mountain, all these factors come into play. You can have water lane deposits, deposition on there. In fact, in the fans that we've observed, there are deposits that are water lane as well. Okay, so we have the fan. Now about the layering within them that we observe in outcrop. I haven't sketched it here, but fans have layers that changes through time create layers within these fan deposits. And this primarily is from climate. Changes in climate will affect the deposition, which in turn creates a layer. Also, if you think about it, this mountain is being eroded down through time, and it erodes into different types of rock on the mountain. So you have a change in source material that can also create a layered deposit within that alluvial fan. Okay, so now to the fun one. The dips, the changes in the dips that we see in outcrop. Let me comment about what you actually see in modern fans and certainly ancient ones. The dips up here close to the mountain don't really get beyond about 15 degrees. Yeah, they can get maybe up to 20 right up at the heights. And then the dips get less prominent as you go out further and further into the basin. So really the most you should see is maybe 20, and kind of an average on the upper parts even would be more like 10 degrees or even less. So this is interesting, isn't it? Because we're observing very steep dips. How does that happen? Well, we often think of things too simply. We say, oh, the mountain uplifted and then the fan developed. Yeah, okay. But wait a minute. Did the mountain just uplift and then the fan develop? If we really think about it, how long does it take for a mountain to uplift? Well, in these parts, in the Laramide orogeny, we're able to date that, and it's somewhere around 15 to 20 million years of time for these mountains to uplift. And that is the key. Let's think about this in steps initially. The mountain uplifts some, the fan develops at the normal slopes you'd expect. Maybe at the max, 15 degrees up in here, 10 degrees up in here, and 5 degrees out there, something like that. So you develop this fan. Well, what happens when the mountain uplifts some more, especially if it's in a pulse? So the mountain uplifted, stopped for a period. Then it took off again. Well, it's going to rotate, of course, all the layers within this fan. It's going to push them up and it's going to steepen them. And new deposition at the proper angles, we'll say of 10 degrees, comes out on that fan over the top of that. And that can happen many times. And the uplift of this mountain can be quite complicated. It might be relatively continuous, then suddenly, boom, a big jump. Not only that, these fans can be used to understand the uplift maybe along the mountain front. The Beartooths have these alluvial fans scattered all along them. You could study these fans if you have material to date, meaning volcanic ash. You could study these fans and learn, for instance, that the north end of the Beartooths uplifted before these did. Or the north had a pulse here, and then the middle was quiet, and down to the south it uplifted too. Or, all these interesting complications that you can unravel using the humble alluvial fan.
Now we can look at the outcrop with new eyes. The layers that are dipping so steeply were originally at about, say, 10 degrees or so, 10, 15 degrees when the fan formed. Then the mountain uplifted just after the deposition of the green line there, somewhere in there. It uplifted dramatically and rotated all these layers to 70 degrees or so. Then new deposition occurred. And then some more uplift probably occurred again, rotating even the new deposition which we see at the upper end here, from say 10 degrees to 20 degrees.
What an adventure this has been, and who would have thought that these mountains here were deposits of alluvial fans, and that these layers of rock that we're looking at used to go way up on top of the mountains. And this is just a remnant. Everything's been eroded away, but these two mountains and a few others scattered along the Beartooths. It's been a lot of fun. I hope you've enjoyed it. Thank you for watching.